Okay, so today we are going to talk about the directional derivatives or the partial derivatives. As we have talked about in the section for limits and continuity, we are going to have similar troubles when we are talking about derivative, because remember, this time you have more than one independent variable, sometimes two, sometimes three. So when the question is being asked, take the derivative, your primary concern is going to be, I'm taking the derivative with respect to which variable? So what we will end up doing is we're going to take derivatives with respect to each of these independent variables. For example, in my first function, I'm asking you to use the limit definition of partial derivatives to find f sub x, x comma y and f sub y, x comma y, where f sub x, x comma y means it is the partial derivative with respect to x. Partial derivative with respect to the independent variable. So x is f sub x, or we will also write it as del f, del x, or if I'm doing with respect to y, we're going to call it f sub y and del f del y. Now, if you have more than x and y as independent variable, for example, if it is a function of three variables, x, y, z, then you can do the partial with respect to z as well. So this question is asking you to use the limit definition. So it's like the first principle of the limit. So we have it on our lecture note, but I'm going to rewrite the definition. So when I'm finding fx, I'm dropping the xy terms. So when I'm writing fx, I'm going to say that this is equal to limit the change in x goes to 0. So limit delta x goes to 0. And on the top, I say f of x plus delta x, comma y, minus f of x, comma y, and over the change in x, so that's delta x. That's the formula. And we're going to evaluate this thing. So let's see what we get. So I say limit delta x goes to 0. In place of x squared, I will have x plus delta x. So I will say x plus delta x whole to the power 2 minus 5 times x plus delta x times y, because I'm not changing y, plus y squared. So those are the terms that are not being changed, all over delta x. The rest is simplification. So you will get to say this is limit delta x goes to 0, x squared plus 2 times x times delta x plus this quantity delta x raised to the power 2 minus 5x minus 5 times delta x, and both of them are getting multiplied by y, so I'm going to do that, y and y, and then finally I have y squared. And this is on top of delta x. So further simplification should be done. Let's see whether there are terms that I can think of cancelling out. So I will get limit delta x goes to 0. And when I say let's think about terms that you can cancel out, you need to go ahead and do a little bit of work here. Remember, this was only the term when I was inputting x plus delta x in my function. So I still need to do minus f of xy. So I'm going to do it now. I will extend it. So this portion that I have done, it is f of x plus delta x comma y. So now you do minus f of x comma y, and that is going to give you x squared minus 5xy plus y squared, where none of x or y has been changed. So I have to have that in my second simplification line as well. So what I'm going to do, I'm going to distribute this minus and get minus x squared plus 5xy minus y squared. Okay. So now it is going to help me cancel a bunch of terms. As you can imagine, positive x squared, negative x squared cancels. I have 2 times x times delta x. I cannot do anything with that. I cannot do anything with delta x whole to the power 2. But the negative 5xy and positive 5xy are cancelled. have to keep the minus 5 delta x times y term, but the y square terms are cancelled again. And this thing is on top of delta x. Well, let's see what we can do with that. So, if you look at the numerator, there is at least one delta x that is common in all of them. So I'm going to say limit delta x goes to 0. Factor out that delta x, and you get 2x plus delta x minus 5y on the top, after I factored out the delta x over delta x. Since delta x is going to 0, it is not equal to 0. Very important to understand. So I can divide it from the top and bottom, cancel it, and you get limit delta x going to 0, 2x plus delta x minus 5y. Well, direct substitution of delta x equal to 0 will give you 2x minus 5y, which is going to be the partial derivative of the function f with respect to the variable x. And I'm going to repeat that word for y, and then we will talk about general rule for partial derivatives. All right, so let's try to do the work for y now. So I'm going to say I'm finding f of y, which by the formula is going to be limit. This time you're supposed to change y and don't change x, because you're trying to see the change in slope when y variables are changing. So how do I write it? I write it as x comma y plus delta y, slight change in y, minus f of x comma y all over delta y. And then you recall your function and start inputting values. So the function was x squared minus 5xy plus y squared. So I'm going to go ahead and write limit delta y goes to 0. X squared, since my x is not changed, I'm just going to say x squared. Then I have minus 5xy, so I will get minus 5x not changed, but y will be y plus delta y. And then I had, at the end, if you recall, you had the y squared term, so that is going to be included here as well. But this time we have to be careful as y is changed to delta y. So this portion is f of x comma y plus delta y. As usual, I'm going to write down the f of xy term, which is subtracted. So that is x squared minus 5xy, and then plus y squared. And all of that is on delta y. Simplification. So I'm going to go ahead and say that this is limit delta y goes to 0. Remember, your x terms are not changed, so those are the easier ones, minus 5x. But then you are going to say that it is going to distribute over y, so I get minus 5xy. I will also get minus 5x and distribute over y, so I get delta y. And then I have y plus delta y squared, which I'm going to write as y squared plus 2 times y times delta y, and then plus delta y. I'm going to raise it to the power 2. Minus all those terms, minus x squared plus 5xy, because I'm distributing the minus y squared. And all of that is on delta y, changing slightly. So when I put delta y factored out after simplification, for example, you can cancel the x squared, you can cancel the y squared, cancel the 5xy terms. So what I will end up having is limit delta y goes to 0. And then I will factor out the delta y, and I will get minus 5x, and I will get plus 2y plus delta y. So these are the only 3 terms that has delta y, which are going to be contributed. The rest of the term are just going to be cancelled over delta y. Again, recall, delta y is approaching 0, so delta y cannot be equal to 0, and since delta y is not equal to 0, I will be able to cancel it from the top and bottom, and my limit is going to be limit delta y approaching 0 minus 5x plus 2y plus delta y. I can do the direct substitution, and hence my answer is going to be minus 5x plus 2y, which again is the partial derivative of the function y with respect to the variable y. And hence we are done using the principle of the formal definition of derivatives, partial derivatives, in executing and finding partial derivatives. So the next topic that we're going to talk about is general rules for finding partial derivatives, and we will see how similar it is to find the partial derivatives as we have already done in Calculus 1. Okay, so let's start talking about these general rules. So this second problem that we have on the handout, it is asking us to find the partial derivatives for a given function in two variables, x and y. And the first one says find del z del x. So find the partial with respect to x. So what do? You treat the y variable as a constant and use your regular derivative rule from Calculus 1 and 2. So let's try to do that. So my z is equal to 20 y squared. I'm sorry, I'm writing 0,2 for 20. So it should be 20 y squared, square root of x. And as I said, I'm going to do del z del x, so derivative with respect to x. So y is constant, it is not changing. So I will say, well, this is 20y squared. All of that is a constant. And I'm going to take the derivative of square root of x, which is going to be 1 over 2 times square root of x. And simplify that, you will get 10 y squared over square root of x. And that is going to answer your question for del z del x. Similarly, when I'm doing del z del y for the same function, I'm treating my x variable not changed or constant. So I would rather go ahead and say that this is 20 times square root of x. That's the constant part in your function. Take the derivative of y squared, which is 2y, and hence you get 40 y times square root of x as the derivative with respect to y. So that is pretty simple. And the rest of the problem in this chapter are going to be just complicated version of finding partial derivatives, and sometimes more than one derivative. We will do higher order partial derivatives as well. So this function is f of xy equal to xy over x squared plus y squared. You find both partials with respect to x and y. So first we're going to find fx. So how do I treat this thing? Well, think about this entire quantity as a function of x only. So y times a constant. I still have x on top and bottom, so I must use the quotient rule. So that will say that you do the square of the bottom. On the top, you take the derivative, so which is going to be y, that's the constant. Derivative of x is 1, so I just get y, times the bottom, which is x squared plus y squared, minus. Now you take the derivative of the bottom, which is 2x. Because derivative of y squared will be 0 as it is a constant. And then I multiply the top, which is xy. Simplify. So you get, on the top, yx squared plus y cubed minus 2yx squared all over x squared plus y squared all to the power 2. So after simplification, I get y cubed minus 2yx squared all over x squared plus y squared all to the power 2. And that is my partial derivative with respect to x. How about the partial derivative with respect to y? So same thing. You're still using quotient rule because top and bottom both has y quantities. So I will say x squared plus y squared whole square, the bottom square. Top I take the derivative with respect to y, so I get x times the bottom, which is x squared plus y squared, minus derivative of the bottom, so I get 0 plus 2y, so that's basically 2y, derivative of the bottom, times the top, which is xy. And you get x to the power 3 plus xy squared minus 2xy squared. Again, I'm going to simplify that. and I will get a pretty similar term as of the last one, and I will get x cubed instead of y cubed, and minus 2xy squared instead of 2yx squared. The bottom is still the same, x squared plus y squared all to the power 2. And that answers your question about finding the partial derivatives with respect to x and y. Now you find the partial derivative and evaluate them. So we'll start by finding the partial with respect to x. And again, y squared is the constant term. Don't do anything when you are finding the partial with respect to x. Derivative of e to the power x is e to the power x. You do derivative with respect to y, so I will first write it here, e to the power x times y squared. Whereas derivative with respect to y, e to the power x is the constant, derivative of y squared is 2y. So I get to say this is 2y e to the power x. And then finally, we're going to input values. So f of x at natural log of 9, 2 will be equal to y squared e to the power x. So e to the power natural log of 9 times 2 squared. Remember, e to the power natural log of 9 is 9. 2 squared is 4. So that's 36. So that's my answer for the first one. F sub y evaluated at natural log of 9, 2 similarly is going to be e to the power natural log of 9 times 2 times 2. That's 2y. So you still get 9 times 4, and that's 36. So the values when evaluated at this point, natural log of 9, 2 is equal. Doesn't necessarily mean that at every single point the partials are going to be equal. In fact, most of the points, they will not be equal to each other. So we'll proceed to our next example. This one is asking you to do similar work. The function is arctangent of y over x. So we're going to find fx, and recall that fx is derivative with respect to x. Derivative of arctangent is simply 1 over 1 plus y over x whole to the power 2. That's derivative of arctangent. Think about chain rule. Now you're going to multiply this thing by the inside. The inside, y is a constant, so you're taking the derivative of 1 over x. So if it helps, write it as y times x to the power negative 1 and do the derivative of this thing with respect to x, which I write by saying d dx. Well, what does that mean? This is going to be 1 over 1 plus y over x whole to the power 2 times, remember this derivative, you're going to get negative y is a constant, negative y because this minus power will come in front, and I will get x to the power negative 2. I'm done with the derivative, simplification. So I will say that this is 1 over 1 plus y squared over x squared times negative y over x squared. That's x to the power negative 2. Which is equal to 1 over x squared plus y squared all over x squared when you find the common denominator and combine terms, times minus y over x squared, which is equal to x squared over x squared plus y squared. That's reciprocal of the bottom, times negative y over x squared. And I can clearly see that the x squared terms will cancel each other, and I will get negative y over x squared plus y squared. And that's your partial derivative, which we are going to evaluate at the point 5, negative 5. So I say f of x at 5, negative 5 will be equal to minus y is negative 5 over 5 squared plus negative 5 squared, which is going to be 5 over, the bottom is 25 plus 25, which is 50, and that's 1 over 10. That's the first answer. Do the same work now, but this time you're doing it for the partial derivative with respect to y. So fy. Okay. So when I'm finding fy, I'm doing derivative with respect to y, but I still need to do the arctangent part. The derivative is going to be 1 over 1 plus y over x all to the power 2. Then when I do the chain rule for the inside, think of that. That portion is so much easier now because x is a constant. You are essentially taking the derivative of y over x, but with respect to y. So I'm writing it, but in future we will keep writing this dy. We'll directly do the derivative. So this is going to be 1 over 1 plus y squared over x squared, as we have seen last time. At this time, 1 over x is the constant, it comes out. Derivative of y is just 1. Well, we have seen that this first portion can be simplified as x squared over x squared plus y squared, and I'm multiplying it by 1 over x, which is going to be x over x squared plus y squared. Finally, we're going to input the value 5 comma negative 5. So f of y at 5 comma negative 5 will be equal to 5 over 5 squared plus negative 5 squared, which is equal to 5 over 50, and that's 1 over 10 as well, which finishes this problem. So let's go do the rest of the problems on this lecture note. This is where we're going to do the partial derivative, and it is for 3 independent variables now. So we're going to find fx, fy, and fz. So let's start with fx. That's the derivative of this quantity with respect to x. I still need to do quotient as both top and bottom has this term. So I will say bottom squared, x plus y plus z squared. Derivative of the top is just y times the bottom, which is x plus y plus z, minus the top times derivative of the bottom is just 1. Look at the bottom, there is only one x term, the derivative is 1, the other 2 terms derivatives are 0. So I got xy plus y squared plus yz minus xy all over x plus y plus z all to the power 2, which simplifies as y squared plus yz over x plus y plus z all to the power 2. We'll do the similar work for fy now. So that's derivative with respect to y. So derivative of the top is x times the bottom, which is x plus y plus z, minus the top times the derivative of the bottom is still 1 because you are taking the derivative of only y now. And that means this is on top of x plus y plus z whole square from the quotient rule. So that will simplify as x squared plus xy plus xz minus xy all over x plus y plus z all to the power 2, which is equal to x squared plus xz over x plus y plus z whole square. The final one is with respect to z, and that is interesting because there is no term on the top concerning z. The derivative of the top is 0 times the bottom, x plus y plus z, minus x times y. The derivative of the bottom is 1. This time I'm taking the derivative of z all over x plus y plus z all to the power 2 from the quotient rule. So simplification is a little easier in this one. It's just going to be equal to minus xy on top all over x plus y plus z all to the power 2. Finally, we're going to evaluate all 3 of these expressions at the point 3, 1, negative 1. So f of x at 3, 1, negative 1 will be equal to, if I look at the simplified form, I'm doing y squared plus y times z over x plus y plus z all to the power 2. And I will just execute the bottom only once because the bottom in all 3 of them are the same. So this becomes equal to 1 minus 1 on top over the bottom is 3 squared, which is 9. So I get 0 over 9, and that is equal to 0. How about f of y? F of y at 3, 1, negative 1. As I said, I know the bottom is going to be 9. So just the top. And the top is going to be x squared. So you do 3 squared. So let me do it one more time. 3 squared, and then you have plus x times z, so plus 3 times negative 1. So the top this time is 9 minus 3, which is 6 over 9. So simplification will tell me that this is 2/3. Finally, I do f of z now, and f of z 3, 1, negative 1 will give me x times y, but negative. So 1 times 1 over 9, which is equal to negative 1 over 9. And those are the 3 required answers for my question. Okay, there's one more problem in this handout, which is repeated partial derivatives. So when I say del 2, del x2, just like d2, dx2, it is the second order partial derivative of the function with respect to x. In order to execute that, you're going to first take the derivative with respect to x. How do I write it? I say del z del x first. So do the derivative of the given function with respect to x. You get 4x cubed minus 3y, and the 5y cubed term will be 0. It's a constant with respect to x. Then you do the derivative one more time with respect to x. So del 2z del x2. And that is going to be 12x squared. Again, y terms are 0. So that's the answer to the first one. So this is going to be 12x squared. The next one is del 2z del x del y. So what do I understand from that? This is the one that I will do first. So first I'm going to find del z del y. So derive the function with respect to y, and you are going to get x to the power 4 goes to 0. You will get minus 3x plus 15y squared. That's the derivative. Minus 3x plus 15y squared with respect to y. Then I derive it one more time, so that becomes del 2, and I derive it this time with respect to x. So del 2z del x del y. So look at your function del z del y, take the derivative with respect to x, and you get negative 3. So that's the second one. It is going to be negative 3. I do del 2z del y2. So del z del y is already there. Derive this thing with respect to y, and you will get 15 times 2, 30. So it's 30y, and that's your answer. So this is going to be 30y. And finally, I have del 2z del y del x. So del x is the one you have done first. You have taken the derivative with respect to x, which I have, which is here. Then you do deriving one more time, so del 2z. Now I derive del z del x with respect to y. So I get del 2z del y del x. So look at this term derived with respect to y, and you get a negative 3. And that's your answer to the question. So as you can notice in this problem, my del 2z del x del y and del 2z del y del x, both of them are equal, which is not necessarily the case for every function. For nice functions like the one that we have, which is almost a polynomial function, you will get this situation where del 2z del x del y will be equal to del 2z del y del x. That means it doesn't matter which variable you have derived first and which one you have derived second. But in other functions, those two numbers might not be equal to each other, which is going to bring up to the concept of a total derivative. Remember, these are called partial derivatives. Next time, we'll talk about total derivatives. But in the meantime, please keep working on your homeworks on chapter 13.3, and we will talk about differentials and total derivatives next time.